Welcome all of you this course on fluid mechanics. As you know it, we have now in the last chapters. The chapters is on incompressible viscous flow through pipes. Before starting this course, let me tell you that when starting the industrializations, the most important things is required to design the pipe networks. Pipe carries gas, the liquid. You need to design an efficient, energy efficient systems for transporting gas or the liquid from one place to other place. So, these chapters what I am going to teach you is very complex chapter, but you can understand a way conducting a series of experiments in the universities in Europe. They make it these chapters quite interesting and they solve the problems, and by the solving these problems they design efficient, energy efficient pipe networks for transporting fluid from one place to other place. Because of that, if you know, today we have a transportations of gas networks, you have a transportations of liquid from one place to other place, the water pipe network, all these design is possible because of these the combinations of experiment works and conceptualizations. So, that's the reason it is a very interesting chapters, and this is the last chapters in my series of the lectures here. Let us start with this considering these chapters I have emphasized on new book, that is what Irvin H. Sames books, which exclusively for this flow through pipes, and other books also we have a Sinjan Simbala and F. F. White. So, what will today I will do it again, I will repeat this virtual fluid ball concepts, so that it can be used for understanding the turbulence flow, which is otherwise it is very difficult to understand what is a turbulent flow and how the turbulence are exchanging the momentum from one layer to another layers. So, I will introduce again virtual fluid balls, then we will talk about the difference between laminar and the turbulent flows, and we also will talk about how these mass momentum flux transported from one layer to another layers, and the time average concept, that what we will also discuss it. Then we will go for the head loss in pipes, and followed by the experiments what is conducted to simplify this energy losses part by conducting a series of experiments with commercial pipes or sand roughened pipes, that what we will discuss thoroughly. After that, we will have the summary. So, today we will start from virtual fluid ball concepts. Let us before that, if you look at this turbulent flows, okay, most of the places we will have the turbulent flow. If you look at the conditions of very high Reynolds numbers, you can show this turbulence phenomena, the hotspot of the turbulent structures what is going on. Exactly same way you can see the turbulent structures, what it happens when you have a waterfalls. Okay. So, you have the transitions, then highly turbulent zones, then you have a low turbulence zones and the high turbulence and the low turbulence. Very close to this could be the laminar conditions. So, most of the that means you can see it these natural conditions where you have a transitions, high turbulent zones and low turbulent zones. So, we will try to know it how this turbulence playing the role for energy dissipations, mass transport and also the momentum transport mechanisms. Now, coming to the virtual fluid balls. As I said it that earlier, we are looking to conceptualize the fluid mechanics, considering there are series of the balls are moving from one place to other place. If I have a different fluids, I can have a different color of the balls, different size of the balls, different mass of the balls. So, that is what we discussed earlier, but this part today I will emphasize that when you have a turbulent flow, mostly you can imagine is that these fluid balls are going to disintegrated or integrated depending upon this turbulence behavior. That means what I am talking about, that if I have a ball is coming it, if it is the high turbulence zone, this ball will be split it disintegrated to number of smaller balls, and these smaller balls will move with a different velocities and they may carry certain mass fluxes. The similar way, if I have two balls are moving it, so if they are disintegrating it, they will have the disintegrated ball, the smaller balls which are disintegrated, there will be exchange of mass flux, also exchange of momentum flux. That is what we will go through it. If imagine is that there is the virtual balls, whenever we have a turbulence zones, at those zones this ball disintegrates. As they disintegrated, there is exchange of mass fluxes as well as exchange of the momentum flux. And if you visualize that two balls are moving it and they are coming closer to the turbulence zone where they themselves disintegrated, as they themselves disintegrated, there will be the exchange of the momentum flux, the mass flux. And if you take a particular horizontal line, then you can visualize that there is a momentum flux and mass flux that's going on, and that what making a turbulence flow behaviors. Or if you thinking that, let us assume is that I do not have a two balls, I have hundreds balls or more than 100 balls. Then what will happen is that not only will be disintegrated, and these disintegrated the smaller balls, they can group them and create some sort of vortex format, which we call eddies. There will be some sort of eddies formations will form it. That edge equivalent, that 4 and 5, the smaller balls, they are grouping together and they are rotating it, and that what type of the eddies formations can happen it. So, let me repeat that things, that when you have the turbulent zones, the flow what is going in, this ball start disintegrating it. That means the balls become the smaller number of balls will be there, and as they have the smaller balls, there will be a mass exchange, the momentum exchange at different axes. If I conceptually that I have a 100 number of balls or more than 100 number of balls, the same things happens, there is disintegrations. As the disintegration happens, a cluster of the smaller balls, they can make a small vortices, which we call eddies. So, there will be the eddy formations or turbulences generations process which is happening, the turbulence generated, and how it is going to decay it, that process also we will talk about. So, basically you try to understand it that when you go for a turbulent zone, the process changes it, and we will talk about with respect to the virtual fluid balls, and which is having the interfaces, and they have the characteristics for disintegrate or the integrate depending upon turbulence behavior. If a turbulence behavior is more, intensity is more, they disintegrate it. When turbulence intensity decreases, they can again integrate it their things. So, considering this, let us try to have a more discussions on this. Let us come to the very simple experiments, as you know, Reynolds apparatus or Reynolds experiments, which is very simple experiments conducted with waters, and you have a dye. The last class I saw the Reynolds apparatus, injecting the dye here, then you can visualize the dye movement. That means what? It is the same virtual fluid balls. That means, I am giving a virtual fluid bed of the colors to here. So, as they are moving the straight lines or they are well ordered patterns or the fluid layers assumed to slides over one another's. That is what is called laminar flow. Or other way around, what it happens is that this flow represent us, there is series of the virtual fluid balls, they are moving it, they are exchanging the mass flux, integration disintegration happening it, but exchange of the mass flux and the momentum flux, it is not that significant order, it is not that significant order. So, because of that, again it comes to the viscous force still dominates, it comes back to the same positions. So, we will have a colored dye when you put it or you put the virtual ball which moves very smoothly, like these smooth layer formations happens it. So, because of this is a laminar flow. But if we increase the flow velocities, other components like Reynolds numbers we will discuss more, then what we will observe is the color dye will not have a flow like a lamina, like layer and layers. There will be try to go deviated, again deviated, again deviate like this. So, when you have these conditions, then we call transition stage. That means what it happens? As we increase the velocity of the flow, in this case we are not changing the density, we are not changing the flow, the mu value, the dynamic viscosity values, only you are changing the velocity. As you change the velocity, that means you change the inertia force. The ratio between the inertia force and the viscous force, that is what increases. As it increases, the balls what is moving it, if I look it in terms of virtual fluid balls, then what it happens it, they also start disintegrating. Start disintegrating, but still there is a viscous force dominated is there, they again integrate it. That is the reasons we have a fluctuations here, against go that fluctuations and like this. So, we can see the colors are trying to diffuse it, again streamlines that. So, in this is the processions, then we call transitions flow. So, that regions is intermediate of laminar and the turbulent flow, which consider is a unstable type of the flow, because it occurs for a very smaller range of the Reynolds numbers. So, that is what is unstable type of that. Then we have the turbulent flow, okay, which we many of the textbook is called chaos flow, it is chaotic process is what it happens it. But let us try to understand many of the process in nature process also behave like this. Okay. It is not only the turbulent flow, we need to have a mathematics to understand this process. As a undergraduate courses, I am not going to that levels, I am to simplify you to learn the fluid, the turbulent flow as a virtual fluid ball motions. I am not going beyond a mathematical treatment of turbulence flow, what we generally do for postgraduate students. That is what I am not going for, that if you look for the turbulent flow is achieved when fluid undergoes irregular fluctuations and mixing. That means what it happens is that when you have the color dye you put it, so it start having very irregular motions. Okay. If is that, what it indicates, if you in terms of virtual fluid balls, they start disintegrating it. They start disintegrating it. So, as there are 100 balls are moving, they are disintegrating and all the things. So, you start having a irregular fluctuations part. That is what we will go more details that what type of happens it. Okay. So, basically when you talk about the laminar flow, it is irregular molecular motions, macroscopically well ordered flow, but macroscopically it is a fluctuating velocities superimposed with well ordered mean time average flow. What do you mean by that? We will go more detail on that. Now, if you look at that, when did these transitions happen from laminar to turbulence zone, laminar to transition zone. That what we call the critical Reynolds number. The transitions, the threshold of the Reynolds number, that what is changes from laminar to transitions and transitions to the to turbulent flow. If you look at that, the Reynolds conducted series of experiment on that for different type of diameter of pipe, different fluid properties like different density, the dynamic viscosity. Then what he found it, if you compute the Reynolds numbers, which is the ratio between inertia force by viscous force, that means rho v d by mu. Here we consider d is characteristic length, and in this case, because we are talking about the pipe flow, the characteristic length we consider is here the diameter of the pipe. So, the Reynolds number in terms of diameter will be rho is the density, v is the average velocity, and the d is the diameter of the pipe, and the mu stands for dynamic viscosity of the fluid. If this is the conditions, what we have seen is that the Reynolds numbers, when it is below 2300, then the flow is laminar. What do you mean by that? If I write this Reynolds number is equal to inertia force by viscous force, that means when the inertia force will have a lesser than the 2500 times of viscous force, then flow becomes laminar. When this is more than that, then it starts the transitions, and further another threshold it comes about the 4000s, which will transitions to the turbulent behaviors. So, these thresholds what we are talking about, it is a linked with Reynolds numbers, which is a functions of or the of inertia force and the viscous force. So, if you can see that there is a dominance comes for a particular level, after that the inertia forces is so large as compared to the viscous force, it start virtual fluid balls as a disintegrated level, or the fluid start fluctuating. This inertia force is so high as compared to the viscous force, then it start going to have a the turbulence natures it comes it, the fluctuating velocity components it comes to pictures. Reynolds numbers less than 2300, it is laminar flow, and then it comes a transition phase. Reynolds numbers greater than 4000, it is turbulent flow. Now, if you look at, if I have a instrument to measure the velocity in the turbulent flow, previous class we shown the instrument like acoustic Doppler velocity meters, where you can measure the velocities. When you in a turbulent flow you measure the velocities, what do we get it to this type of curve you get it, the fluctuations component. Okay? So, you get the fluctuations component. That means, the velocity what you get it, it has a two components. One is the average velocity component, another is fluctuating velocity. So, you really the turbulent flow, whether in a pipe flow or the channel flow, if you measure it, you will see this type of fluctuations in u scalar velocity v and w, they are in x, y, z direction respectively. So, in that case what you are doing, that each the velocity components having the fluctuating velocity component, and here I am considering the steady flow, steady turbulent flow. In this steady turbulent flow, it is not unsteady flow, this is steady flow conditions, also we get it the velocity fluctuating components in y directions, v directions and w direction, that means x, y, z. So, when you comes to turbulent flow, do not show only u, v, w, you should show three components, that is fluctuating velocity components, which is varies instantly, instantly at that measurement locations, and you have a time average velocity component, and this the velocity of u, which is the a particular point the velocity u is equal to average velocity and the fluctuating velocity. The summation of that is represent u. So, these are the fluctuating velocity. Now, you can ask me that how do you compute average velocity, the time average velocity. The time average velocity we compute like 0 to t into u and dt. That means, we time average or time integrated the velocity component, we integrate over the t domain and compute it what is average velocity. To know it, if there is no fluctuations components, the average is the velocity is going on, time average. This is called time average velocity component. Then what is that? Plus you have a fluctuating component. If you look at this, if you just look at any of census data, also fluctuates like this. Daily to daily, if you look the census data, the economy census data, most of the shareholders they look it, they also fluctuates that. So, many of the process when you try to understand it, it has a average behavior and the instantaneous fluctuating components. In nature we get it similar way, in a turbulent flow we have time average velocity component and the fluctuating velocity component. Now, if you look at the physically or the conceptually, if I have a two balls which are disintegrating, because their inertia forces is much larger than viscous forces, what is happening in the fluids. If that is the conditions, as I said it earlier, it will be disintegrated. As it disintegrated, you will have a mass flux change and the momentum flux change. Those quantities can give a additional mass components. If you are looking at the layer level, additional momentum flux component. Those things will detail we discuss it. So, that way again I need to summarize that in case of the turbulent flow, we have two components. One is a time average velocity component, another is fluctuations velocity component. As similar to if you look at a economy data with a census data, all behave like these behaviors, because there are different process works at the different levels. Now, if you look at, if I consider is that there are three velocity components, okay, in x, y and z directions. If I have three velocity component, if you wish to compute it, how much additional mass flux is going on? Additional mass flux due to the fluctuating u dash component in the x direction per unit area. All these components were per unit area. Then as you know it, rho u dash you will get it. So, this is the mass flux is coming as a fluctuating velocity is there, or we can try to understand from this after they disintegrated that component of the disintegrated virtual balls is giving a additional mass flux in the x directions. That what will be the density times of velocity. That is what you will get it. Similar way you can have a y direction and the z direction. This is what we are talking about, additional mass fluxes will be there because of. Do you remember that this u dash component, the fluctuating velocity component can be positive directions or the negative directions. It can move in any of the directions. So, that means mass flux can go out or come in. Okay. You can try to understand it. A mass flux, if you are computing in a particular layers, can come in or go out depending upon the directions of u dash. The similar way, if you look at this, the mass flux, additional mass flux which is coming due to the fluctuations components of v dash, W dash will commit to that. But same way, if the mass flux is going on in area, so you will have a momentum flux, that mass flux into velocity, and this momentum flux, because of u fluctuations, you will get in x directions, y direction, z direction. Having this free velocity component, you have a momentum flux, that is due to only fluctuations component. Due to the disintegrated of the virtual fluid balls, their additional momentum flux is coming in, and that has a three components, x and y, z directions. Because of the fluctuating velocity component, we generated the mass here and the corresponding momentum flux. Same way, we can find out what could be the momentum flux due to the fluctuations of V A dash in the x directions and the y and z direction. So, you can write these components very easily, just you look at the notations, you keep it track of that, the notations. Because of that, I always advise you to draw this type of axis, then you write the u dash v dash component and rho u component, dash component, and all you write it, and then you can understand it. There is a mass flux is coming, momentum flux is coming, and all. So, but here also, because we are not worried about the fluctuations components at that instantly, we look at also a time average concept. So, same way we are giving this the bar to represent these are time average momentum flux. Okay. So, you can write it, if there is a momentum flux, there is a force or the trace components are there. So, we will discuss that in the next class in terms of afferent trace components. So, if you can try to understand it, because of this the fluctuating velocity components, now we have a time average the momentum flux in x, y, z directions because of the fluctuating velocity component of this. So, additional force component or additional stress components we are getting it because of fluctuating velocity component. So, that is the reason if you have a steady laminar flow, the steady, it does not change with the time, you can see the velocity and the time will have a more or less constants, it is a steady flow. But the steady turbulent, you will not have a constants, you will have the turbulence natures. If you look at this, it is very easy to draw turbulence behavior, because it is a randomness is there, chaos is there. So, it does not follow the patterns, so it is easy to draw the chaotic patterns, because as you like you can sketch it. So, that way it has the turbulence, the chaotic behavior with a steady flow. But if you have an unsteady flow, that means velocity varies with respect to time, your time average velocity is varying it, and over that you have a fluctuating velocity component. It is quite interesting. So, this is a unsteady turbulent flow, this steady turbulent flow, this is steady laminar, and already we discussed it because of these fluctuating velocity components, how much of momentum flux is there, what is the mass flux is there, and this change of the momentum flux which indicates for us there is change is force components, or as equivalent force per unit area is a stress component or afferent trace component. We will revisit again to give it more time to you to think about this turbulence behavior, because if you understand the turbulent behavior, then really you will appreciate the fluid mechanics. That is my job, you to revisit again turbulence, again talk about the same things with again in a repeating way. Now, if you look at the next levels, if you talk about that, what it happens in turbulence, that if you look at that, I have the pipe flow, I have the pipe flow, and I know is very well is that the no slip conditions happens near the wall. That is what we studied in the first class. So, once you have a no slip conditions, when you have a no slip conditions, then what it happens is that you will have a velocity is equal to 0 and velocity is going to increase from this place.
So, as the velocity increases, then what it happens, because this is turbulence nature of the flow, there is a generation of eddies. As I said that in terms of virtual fluid balls, the fluid balls are goes as disintegrated and they group themselves, they create the eddies, okay, which is not visible by naked eyes. Okay, don't think it that these are all conceptualizations. So, when you have this the eddies formations, these eddies becomes bigger and bigger size, bigger and bigger size, that is what is happening. Okay. But they are the low frequency component. Then they disintegrated into a smaller eddies. Okay. The number increases, the high frequency component, the number of the smaller eddies much larger. But when the eddies are smaller, then you have the viscous components which reduce it and dissipated the eddies formations. So, that means always a energy cycles goes on, like you have a very high flow, the turbulence generated, it generate the large eddies, then again it split it into the smaller eddies, the smaller eddies again dissipated it due to the high viscosity zones. So, there are the zone of turbulence generations, the decaying it, energy cascading and the dissipations. So, we are not going more details as I said it earlier, but try to understand it. When you have the turbulent flow, your energy dissipations, the mass flux computations, the momentum flux computations, because of the fluctuating velocity components, we are getting additional terms and which are very complex process. If you have a very complex process, only options is left to us that you conduct series of experiment and you simplify the flow problems. That is what it did it in Europe in early industrializations periods. So, what they did it that to design these pipe systems, like for examples, we have a water supply systems. Okay. So, if you have a water supply systems, there could be a source and there could be the pipe network to different locations. There will be, you can imagine it that can have very complex pipe networks supplying to water to different locations. How to design these pipe networks? So, now it is coming in that we can find out how much energy losses or the head losses in a pipe flow systems. If I know the how much of energy losses here, how much of energy losses here, how much of energy losses here, then I can quantify it, the energy availability at different points. That energy availability will give us the flow is coming or not coming. And that is what we do it. This is quite analogous to your power transmissions, electrical power transmissions line, similar way, but here we are talking about the head losses, the energy losses in a pipe network or in pipe flow. Now, come it to that. So, you need to do the experiment to quantify energy losses, and that in terms of head loss, that means in terms of Bernoulli equations point of view, you are talking about head loss, but we are looking at what will be the energy loss part. Now, if you look at any turbulent flow going through a pipe systems, then we can easily make it what are the governing or dependent variable components. Like I have a pipe, as I have the pipe part is going through these, I have to look at the average conditions, the time average P and time average velocity. So, we talk about the time average or mean time average pressure component. We all quantified is in terms of mean time average and Mean time average profiles remain fixed in the directions of flow. Flow is turbulent. The hydrostatic variations is also neglected and fully developed and a steady flow. Okay. These are the simplifications. The mean time average, as I did it earlier, you can compute it what will be the mean time average, and you just integrate V over the delta t, and 1 by delta t will be the mean time average. Or indirectly what you are looking at, that if you have a velocity like this, you are just taking the average velocity, which is the representing the area of this total area. So, that is the average velocity what we are getting it. Now, let us, now what we are doing is first the dimensional analysis. So, if there is a pressure drop along a pipe in a turbulent flow, depends upon the following quantities: pipe diameters, length of the pipe, okay, diameters, the length of the pipe, mu is similar to the coefficient of viscosity, familiar to the coefficient of viscosity, and average velocity, rho, and the small e represents the average variations in pipe radius. Now, you can understand what is that. If you look at the pipe, the different pipe will have a different roughness. Like this glass surface maybe looks for me is a smooth surface, but if you look at it microscopically, there is a roughness is there. That means, if I take this surface, for my hand it may looks like a smooth surface, but microscopically if I look it, there is a roughness is there. Okay. So, if you have a roughness in the pipes, then you have a more turbulence behaviors happens it, more energy dissipates it. Smooth the pipes, less the energy dissipate, the less turbulence behaviors happens it. So, if you look at that, if you have a pipe, we can see there is a smooth pipe, but really it is not a smooth pipe. Even if your glass panels what you have, all have a certain degree of the roughness. So, there is a variations of the pipe radius. The pipe radius, but it could be a sub-millimeter levels what we are talking about. We are not talking about the centimeters which you can see, the sub-millimeter level, 1/10 of the millimeter level, that type of roughness what we are looking at, and that what we are getting it. And if we are getting it, how these things are affecting this, the turbulence behaviors and the energy dissipations. The first, let us look at the dimensional analysis. That means, delta P will be the pressure difference will be the functions of the d, L, mu, v, rho and E. Here E stands for pipe roughness. If you conduct a dimensional analysis, this is a non-dimensional part, this is a non-dimensional, and this is the non-dimensional this. So, the dependent variable non-dimensional form or dependent variable this form we got it, where this is the Reynolds numbers, this is the dimensions of geometry of the pipe, length and the diameters, and this is the with respect to the roughness height and the d. Just these equations, if I further simplified it, that if this L by d, if I come out and make it p rho v square here, the L and d ratio I know it. So, my new function of h, which will be a function of Reynolds numbers and E by d ratio. Okay. So, we are replacing with an unknown functions with h, and which is the functions of Reynolds numbers and the roughness by d, that ratio, and we have a L by d. That is what, if you rearrange it as defined, its head loss is a rho p by rho. If you look at what you are getting it, v square by 2 L by d H L, and there is a functions which is a function of Reynolds numbers and roughness height by the d diameters. These can be considered as a constant, and we define it a friction factors. This is a new definitions we put it, that this constant, it is not a constant, it varies with respect to the Reynolds numbers, with respect to the ratio of roughness height and the diameters, which we call a constant, the friction factors. Because for particular flow systems, you know the Reynolds numbers. For a particular pipe, the type of the pipes, we know this, the roughness height and the d, and since these are known to us, if I conduct a series of experiment in terms of Reynolds numbers and in terms of the roughness height d, we can compute it, or we can get it the friction factors. That is what it was done in earlier, to conduct a series of pipe flow experiment to find out these functions, the f functions in terms of the Reynolds numbers and mu by d. So, if you know these functions, then the head loss, which is the Darcy-Weisbach formula, is this part, which is simple part. Okay. It is easy to remember it. Is that the head loss will be the one is a friction factors L by d v square by 2. Okay. This is some sort of kinetic energy per unit mass. L by d is a geometry factors, and you are multiplying with f. So, you try to understand the head loss is a function of a friction factor, L by d v square by 2 is the kinetic energy per unit mass, L by d is the geometry factors, then f is your friction factors, which is a functions of Reynolds numbers and E by d. So, if I know these functions, I can easily compute it how much of head loss will be there. So, that is the reasons that a series of experiment was done by Nikodous experiments for laminar and the turbulent flow. Series of experiment they conducted for this. Okay. For the laminar flow, what it is found it, the friction factor is just a inversely proportional to the Reynolds numbers, and the constants becomes 64. This is experimental finding with conducting a series of experiment in pipes in a laminar flow. It is found to be the f and the Reynolds numbers in terms of diameters have a inversely proportional, and that proportionality constant is the 64. Okay. So, this is experimental data, and since in terms of Reynolds numbers, so it can valid for any of fluids, that is not a big issue. Now, we talk about the Nikodous data for artificial roughening pipes, which he conducted a series of experiments, and this x axis if you look it is a Reynolds numbers, and the y axis is a friction factors, the Reynolds numbers in a log scale. Okay. So, if you can look at these Reynolds numbers in the log scale, let us interpret this data. These are the experiment data from artificial roughened pipes. That means, what he has done it, he put the sand and glue it, means fix it, sand with a different diameters. So, that way he get lot of roughness variabilities in the pipes, and he conduct a series of experiment because he know this roughness part, he know the d part, and he also know what is the flow Reynolds numbers in terms of the diameter d. If it is this is what the finding of his the experiment. Just to look these graphs, you can interpret many things from this graph. First is the laminar flow zone. Okay. So, it is just going down inversely linearly decreasing trend, inversely proportional, it is going down. Then if you consider a smooth pipe, it increases again decreases. If the pipe is smooth pipe, it increases with the Reynolds numbers, then it start decreasing part. This is quite interesting, that the friction factors which is giving as an indicator of energy losses, because if you look at this, energy losses is F L D by V square by 2. So, if F is higher values, so you have a more the energy losses. So, if you look at that, the energy losses is increases, then it is a decreasing point, and when it is coming a more the higher the Reynolds numbers. Higher the Reynolds numbers, you have a decreasing trend. As you add this roughness, the boundary roughness in the pipe, okay, this is increasing trend. This is the highest roughness part. So, as you increase the roughness, the turbulence intensity increases, energy losses will be the more. That is what it happens, energy losses will be more. And that after certain Reynolds numbers, this is independent of the Reynolds values. It is a constant, it is a parallel line. What do we mean by that? This value F does not depend on Reynolds number. That is what is indicating it. So, more the rough the pipes, what we have seen it, the initially for a turbulent zones it increases, then it becomes steady, then it becomes constant. At that periods, it is independent to the Reynolds numbers, the flow Reynolds numbers in terms of diameters. The intermediate, they have a like a roughness value is a less, you will have a, it will act like a smooth pipe, then the roughness effect will come it. Act like a smooth pipe, then roughness behavior will come, like this the behavior will come it. Let me repeat these things, because this is very interesting data, and it talk about the gross characteristic of the turbulence in a pipe with roughened, artificially roughened with the sand and the glue. Okay? In that case, how this friction factor changes with respect to the Reynolds numbers and the ratio between the roughness and the diameters. This is less roughness to the high roughness zones. As I said it earlier, this is the laminar zones, it is very clear cut, it is inversely proportional. In the laminar zones, as the Reynolds number increases, the friction factors decreases, that means your energy losses is decreases. But when you go for a transitions from laminar to transitions to the turbulent, the smooth pipes behave like this, the rough pipe behave like this. Intermediate, they behave like a partly smooth, partly rough. If you look at these behaviors, try to understand it. What I am to talk about that, whenever you get it the experimental data which really speak about the gross characteristics, we try to understand that very detailed, that how different dependent variables, like in this case the friction factors, with depending upon the two variables non-dimensional parameters is Reynolds numbers and the roughness T, how it is varying it as you commit very complex things. And these things you just interpret it in terms of smooth pipes, that means the roughness very less, and as the roughness increases, how this characteristic or how this turbulence, additional turbulence is generated. That is what the more energy losses is happening, and which is also depends of the Reynolds numbers. After a particular threshold Reynolds numbers, it also does not depend upon that part. I just encouraging you just to visualize the flow. There are many, could be YouTube are there, you can look it at the wall level, at the near surface boundary of the pipe. If you have a rough pipe, how the turbulence is generated, and at particular Reynolds numbers, after that the effect of Reynolds numbers is not there in friction factors, which remains constant. That what you can visualize it when you just think about a gross characteristic of turbulence behavior in pipe flow. Now we have the tabulate values of the pipe. If you look it from the glass to the concrete, this, as you know it, glass will be as smooth as, but still it is have a, in terms of millimeters you have the dimensions, but when you go for concrete will have a dimensions if you can look it. Okay. So, you just look at these diagrams, values, and this part, different type of pipes you have. The concrete pipes for certain case of the transporting some, you have a glass pipe, you have a cast iron pipes, riveted steel pipes. So, all will have a different roughness behavior values. For the commercial pipes, they will have a, so glass pipes are a smooth pipe, as close to the smooth pipe, and as you go for the cast iron, wood stove, concrete, and these, the roughness is increases. So, more the turbulence behaviors happens. Now, this MODI chart compiles for conducting a series of experiment in using commercial pipes, not artificially roughened pipe. So, again plotting with the Reynolds numbers and the friction factors. This side is friction factors. Again I am writing F equal to L by D V square by 2. Okay. So, if you look at that, there is not much difference between the commercial pipes and the roughened, artificial roughened pipes. The characteristics more or less same. Okay. But this is the laminar zones, this is the transition zones. Here you will not have a much fluctuatings of the component of this. Then you can look at the transition zones and rough pipe zones, and these are the relative roughness values what is given it. So, if you try to interpret it the similar way, but here we have divided for the different roughnesses that. Now, let us tell you that how we use these MODI's charts for real applications. For a real applications, first you compute for a particular discharge and the mu and the rho, you can compute what will be the Reynolds numbers, and you know the type of the pipe what you are using and the diameters. So, you know these two values. As I have these two value, what I will do it, let me I have a this Reynolds numbers and I will go for particular E by D, that value will come as effect. So, these graphs are used to interpolate the F value if I know Reynolds numbers and the relative roughness value. So, if I know it Reynolds number, then you straightly go it, find out which curve is representing relative roughness, and that curve corresponding values will give me friction factors. If you look it that way, we just interpret it. If we have a different pipe, different roughness pipes, like as the roughness relative roughness values are increases in these directions, the F value is also increasing trend. So, if you just look it, if a F value is 0.01 to 0.08 means the energy losses will be 8 times higher. If you keeping everything is constant, the energy losses will be the 8 times higher between 0.1 to 0.08, because these are multiplication factors. So, energy losses will be the 8 times higher. So, and we can compute the energy losses if you have a MODI charts, which is the experimentally determine the friction factors from the flow in the pipes. With this, let me conclude today's. First, we discuss about the Reynolds experiments, how the
three different type of flows there: laminar flow, transitions and turbulent flow. We also discuss the virtual fluid balls, how we can compute the mass and momentum flux in turbulent flows. The head losses in pipe, and that's this Weisbach equations also we discuss, and also we discuss about the experimental relationship between friction factors as a functions of Reynolds numbers and relative roughness E by D, and that is what is Modi's chart for commercial pipe, Nicker-Rhodes chart for the artificially roughened pipe. So, with this let me conclude this lecture. Thank you.